Hello students, in this lecture we will deal with the module 5 of engineering physics of Bachelor of Engineering semester 2 of VTU Belagavi. The module is entitled as Materials Science. Module 5 mainly deals with the electrical properties of materials, and we will be learning about three types of materials, namely good conductors, semiconductors and dielectrics. The topics being are divided into three parts. One is quantum free electron theory of metals, physics of semiconductors and dielectric materials. In quantum free electron theory of metals, first we will review the classical free electron theory and its failures. Then we will learn about the assumptions of quantum free electron theory. Mention something about the expressions of density of states. We'll see about the Fermi-Dirac statistics, Fermi factor, Fermi level. We have to derive one expression for Fermi energy also. Then we will just review the success of quantum free electron theory. So in the case of physics of semiconductors, again the Fermi levels of intrinsic semiconductors, some basics of semiconductor we will see, and expression of concentration of electrons in conduction band, hole concentration in valence band, that is just an expression, no derivation there, and conductivity of semiconductors, there is one derivation, and there is one derivation for the expression of Hall coefficient. The last part is dielectric materials. There we will see about the polar and non-polar dielectrics, internal fields in a solid, Cauchy-Moussorti equation, there is a derivation, and then we will see about solid, liquid and gaseous dielectrics with one example. Then finally the application of dielectrics in transformers. Before proceeding to the module, let us know the course outcome, which we know as COs. So in this module, it forms as CO4, it is CO4, and at the end of the course, the student will be able to understand various electrical and thermal properties of materials like conductors, semiconductors and dielectrics using different theoretical models. Those being the course outcome, let us see the module outcome, that is for module 5. At the end of the module, student will be able to review classical free electron theory and acquire knowledge of quantum free electron theory, understand the concept of charge carrier concentration of on the basis of Fermi level, conductivity of semiconductors and Hall effect. 3. Understand the origin of dielectrics, differentiate the types of dielectrics, their examples and applications. And number 4, let us solve some numerical problems also. The module is very interesting to learn, being we are going to learn about the electrical properties of materials, which is one of the very important properties. As you could see, we cannot imagine the modern life without electricity. Okay, let us review some of the historical developments in this regard. Already in 1800, electrical battery was invented by Alexandro Volta. And you see that means there is a generation of current. Generation of current was already done. But people were not knowing due to which factor this electricity is being generated or transmitted. I'm just going to see some of the points here. There are other points are also indicated here which are important milestones in the electrical or understanding of electricity. because you could see that already in 1880 the electrical bulb was invented by Thomas Alva Edison. This also you know. But then the very reason for this electrical conductivity, which we now know as due to the charge carriers, which is mainly the electrons, but then discovery of electron was done in 1897 by J.J. Thomson. So you see that already in 1800 we had the electrical generator, but we had to know the charge carriers in 1897, almost 97 years later. And regarding the understanding of, because this is mainly due to the understanding of atoms, how the atoms are made, regarding the proton, neutron, and electrons revolving around there are something called as free electrons in some of the elements. So those were all done mainly based on the models like Neil Bohr or Rutherford atomic models, and mainly we need to see about Pauli's exclusion principle. This we will see in bit detail when we look into the quantum free electron theory, and also something about wave equation, which you already seen in the other module, that is in module 3. And regarding the electron occupancy and freeness of electron and quantum free electron theories, and quantum free electron theory was developed mostly by Paul Dirac in 1928. Fine, we know that electrical materials could be classified as insulators, conductors, and semiconductors, and these are some of the examples. Wood and glass are insulators, and for conductors you have aluminum, copper, brass, etc. In the conductors, again, if you see about the bad semiconductors or bad conductors, silicon, germanium, etc. And then there are something called as superconductors. It could be any material exhibiting any properties, but everything depends on what it is made up of. So when what it is made up of, all of us know that they are all made up of some basic elements. Elements could be elements are we learn elements in the periodic table. Further, it is interesting to know that in the periodic table, elements are laid on the basis of electronic configuration, and we know that down the group like this, most of the elements have same properties. For example, this is alkali earth metals, alkali metals, and here it is alkali earth metals, and these are the transition metals. Sorry, till here is a transition metal, and here is a noble gases, halogens, chalcogenides, etc. And for a good conductor down the group, to understand, we know that good conductors are copper, silver, and gold. They are placed here down the group. And similarly, the semiconductors, if you consider, then silicon and germanium are semiconductors, elemental semiconductors, which are also present in a periodic table. So periodic table helps us to understand the properties of materials, and we could, even in preparation of the materials also, periodic table comes into great help. In this periodic table, based on the outermost filled orbital, they are classified. As you could see, this is S block elements are present here. So here the outermost elements are d orbital, d block, and then there are p block, and then f block, which are lanthanides and actinides. You may be wondering, why I need to speak about the electrical properties. Why should I speak about the periodic table? As I already mentioned, in the periodic table, elements are placed on the basis of the electronic configuration, and you have already learned in your previous classes that electronic configuration is controlled by basically three rules or principles. They are Pauli's exclusion principle, Hofbauer principle, and Hund's rule, which you know, Pauli's exclusion principle, which states that no two electrons in an atom can have the same four quantum number. Hofbauer principle, filling up is from the bottom up, like lower energies are filled, or inner orbitals are filled first, and then it is going to be the outer orbital. And then by Hund's rule, if multiple orbitals have the same energy, one electron goes into each of them before they start develop or pair. So based on this, electronic configurations are made. Underlying factor for us is that by this exercise of electronic configuration, we will come to know which are the elements with how many electrons present in the outermost shell. Like you could see here, in the case of hydrogen, it starts with the one element, so it is 1s1, so it is just one electron that is present. For example, in the case of carbon, it is 6, so 1s2, 2s2, 2p6, so 1s2, 2s2, 2p2, and 2 electrons based on Hund's rule, one each is filled here. And in the case of neon, it is a noble gas wherein all the shells are filled here. The electrons filled in the outermost shell or valence shell are known as valence electrons. These valence electrons are responsible for some properties of chemical elements. So based on the same rule, we can go on fill for different elements, like for example, you could see here for lithium, sodium, potassium, copper, etc. And for lithium, you see that there is one electron that is present in the outermost shell, and for sodium also there is one, and for potassium also there is one, for copper also there is one, like this. So this is for the silver, and this is for the gold. Based on the number of electrons in the outermost shell, we can classify the elements as metals which are having 1 to 3 number of electrons in the outer shell. Could be A metals, like which are having 4 to 7 roughly, and then noble gases which is having 8. It means here we're just considering a very small number here, where in the very beginning elements in the periodic table. Now let us generalize the element to a solid. Here you consider this as a solid with many elements. This is one element, another element, another element. So elements means I mean the atoms. So made up of several atoms with which is having one electron free in the outermost shell. You see, each element is having one electron in the outermost shell. Further, we generalize it as that the elements or the electrons which are present near one electron, which we already explained as the free electron, that means they are mobile. So we can consider them as mobile, so that means they are not attached to a particular atom. So that means this electron is not attached to the element here, it could be mobile. So this electron is not attached to a particular electron, so they are mobile. So that is why they are called as free electrons. When we say that electrons are mobile, that means we can imagine them like a liquid, or we can approximate them like an electron sea. So electrons are present everywhere, and they are mobile. And when we say that they are mobile, of course they are mobile, but they are not directed, their mobility is not directed to a particular direction. But now you consider the material, that is this is the material with many electrons that is present in the material, and that material is connected to a battery. So when I say the battery, so that means it is an electrical generators. Here let us consider E as the element, A as a field, electrical field, so that is moving in this direction. Okay, so that means it is in the anti-clockwise direction. So it is in the anti-clockwise direction like this. So when this field is applied, it is going to influence the movement of the electrons, which are the charge carriers. Okay, so these electrons will move in the direction opposite to the applied electric field. You see that the arrow mark is here and the arrow mark of the electrical field is here. So that means electrons will be moving towards the positive electrode, and this is how the charge is going to be generated, or the mobility of charge is explained. Which means that we explain the conductivity or electrical conductivity based on the mobility of free electrons. So this concept of free electron is put forward by these two great men, Paul Drude and Lorentz. Let us see some of the milestones in the next. Look at this slide, it should be interesting to you. Picked up some of the important events in the historical days, which were very instrumental in understanding the electrical conductivity. So now you know that discovery of electrons was there in 1897, but then still electron theories were still being developed, and electrical conductivity was still being developed, and this is the Paul Drude. He first told that electrical conductivity is basically due to the electrons, but he considered electrons could be positive and negatively charged. Interesting, isn't it? It is both positive and negatively charged. Further, he treated the electrons as gas molecules. So this is the assumptions. These are all some of the theories that were developed. Later, you see that after 5 years, Lorentz he came forward to say that no, electrons are cannot be positive, and it could be only negatively charges. And moreover, that Lorentz considered the Thomson atomic model, in which electrons are embedded in a positive jelly, which is of course before the Rutherford Bohr atomic models. He called such electrons as free electrons. So you see, so who called it free electrons? It is Lorentz who first called it as free electron. That is why we call this particular theory free electron theory, or Drude-Lorentz free electron theory. Based on this introduction, let us see the free electron theory. First, let us see the classical free electron theory. So wherein we'll just learn about the assumptions. First its assumptions, and then there are some definitions and consequences, and their merits and demerits. So to begin with the assumptions, there are 4 assumptions which were made based on the observations of classical free electron theory. The first one is that it is assumed that the electric potential due to the ionic cores to the metal to be uniform. Here ion core refers to this. These are the ionic cores. These are the ionic cores. Okay. So the electric potential due to these ionic cores are uniform throughout the entire metal. Okay, and they are uniform. Second one is, in a metal there are electrons which can move freely. So that means there are free electrons. Whenever the electric field is applied, the free electrons acquire drift velocity and move in the direction opposite to the applied field, which I had shown in the previous slide, if you can refer back. The third assumption is that the attraction between the free electrons and the lattice ions and repulsion between the two free electrons are considered to be insignificant, because if they are significant, what happens? If they are significant, then the attraction between the free electron and the lattice ion will make them combine together always. There is no free electron for the mobility and there is no conduction. That's why these attractions and repulsions are considered insignificant. So in the fourth assumption, the free electrons in the metal are treated as gas molecules. So these are the free electrons. These are the free electrons. This is the second assumption. You remember, this is the second assumption in the previous slide, that there are electrons which are free to mobile. So in the fourth assumption, it is told that these free electrons are treated as gas molecules. So that means, so these are, all the electrons are present in the entire materials. So they are like a gas molecule. Thus we can apply the kinetic theory of gases, and based on that, in the absence of the field, the laws of kinetic theory, if it holds good, then the energy associated with the electrons can be written as 3 kT by 2, where K is a Boltzmann constant, and it could be related to the kinetic energy half mv square Th. Th refers to the thermal velocity, Vth refers to the thermal velocity. So we have classical free electron theory. And now let us define some of the terminologies which comes in electricity, like mean free path, mean collision time, relaxation time, drift velocity, thermal velocity, and mobility. And most of them you have studied in your previous class. Let us just refresh. Okay, first, the mean free path. Now you need to understand the word mean free path. You understand path. First, path refers to what? Path refers to the distance. Some distance, you call it as a path, and then free path. So that means there is some stretch wherein a movement could be there. Now this is just a statistical word, mean. Okay, so that means by definition, mean free path is the average distance traveled between the two successive collisions. So that means when the electron is moving, so that means it is bound to hit the core elements or the ion cores. So that means collision is inevitable. So between this collision there is some free path that is moved. So the average of such distances or averages of such mean free path or free path is called as mean free path. For example, in the case of copper, it is around 420 angstrom unit, and in the case of potassium, it is 370 angstrom units. Mean collision time. Here also you need to understand the word first. First understand time, Next is a collision time. We have learned in the previous diagram that collision is inevitable. So that means in the previous one we learned that the distance traveled is a free path. Now the time taken to travel such distance is nothing but the collision time. So it is a distance, the time taken between two successive collisions. So statistically, mean of all those distances, we call it as mean collision time. So by definition, it is the average time interval between two successive collisions of electrons with lattice ions. So mathematically you can write it as tau as a collision time, mean collision time, that is equal to lambda by v. Okay. So where if v refers to the thermal velocity and vd refers to the drift velocity, which we'll see later. Next, let us consider the relaxation time. To understand this, let us consider the solid with free electrons, and we supply the electric field. So that means there is a electrons which are moving in the direction opposite to the applied electric field. Okay. Now it is nothing but the time which is taken by the electrons to come to rest position when the field is just off. Okay, that is what is the relaxation time. Mathematically, it can be defined as, to start with, like rate of change of the velocity, that means it is decreasing here, is given by minus V average by tau r. And the decay will follow the expression V average is equal to V average prime into e to the power minus t over tau r. We don't have a derivation here, I am just giving you the equation. Now in this equation you see that the power of E, t and tau r. When this t is equal to tau r, so here tau r is a relaxation time. When t is equal to tau r, so that means in the expression we have this t is equal to tau r, so that means that is e to the power minus 1, and then V average will be equal to V average prime into e to the power minus 1, which if you rearrange, you can write it as V average is equal to 1 over e into V average prime. So this is what we call as a Arrhenius plot, or is the exponential decay, as you could see here, and which is shown in the graph like this. So wherein you could see that when the power is just off, that the velocity or the average velocity is going to drop down like this in the initial time. The initial time interval, if you take, then the decrease is going to be very large. The velocity decrease is going to be very large. Then as the time passes, the decrease is going to be lesser and lesser. This is what we call as Arrhenius plot. Okay, now by definition, relaxation time is the time required for the average velocity of the free electron to reduce to 1 over e times its value that existed when the field is just turned off. Here I am giving a table with the mean free path and relaxation time of a few of the metals. Just consider that for lithium, mean free path is 110 angstrom unit, sodium 350 angstrom unit, potassium 370, copper 420, and silver 570. And these are the relaxation times. For the silver it is 4.1, and for potassium 4.4, etc. Now if you just look into the mean free path, you just have to compare and correlate them for a conductivity property. Out of these elements, which is a good conductor? Of course, silver is a good conductor, and its value of a mean free path is 570. That you see that mean free path is large means that much gap is without any collision. So that means it is a free path. So that means it is with less resistance. So that means conductivity is better. So that is how its good conductivity is explained.